Oh, I just had the hiccups, but here we are, much better, because we're doing maths. So we have a rectangle, wonderful, with a parallelogram, another beautiful quadrilateral inside. So it kind of looks like a flag, but not really. So we're given that the distance from each corner of the rectangle to the next vertex of the parallelogram is x centimeters, right, in the clockwise direction. Right, so there's some symmetry, right? There's a consistent length for that portion. All right. Use calculus to find the smallest possible area that the parallelogram can have in this situation, and we need to justify it. So basically, as we adjust x, for example, if x was a bit larger, so maybe to here, we'd have, okay, that's not what it looks like. Oh, this is harder to draw than I thought. So if we go a little bit further, a little bit further, a little bit further, a little bit further, and then we can connect them up. Oh yeah, that's smarter. Beautiful, beautiful. Notice how the parallelogram has like kind of rotated a little bit, but the lengths are different. We can keep doing that as we change x, and what will happen is the area of the parallelogram will change. Now there's going to be a sweet spot, so an exact value of x, so that the parallelogram has the minimum area, right? It's the smallest possible parallelogram we can make with these restrictions. So we call this an optimization problem. In this case, we're optimizing it to have a minimum area. All right, so that's the context. How will we go about that? So first of all, we need an equation that relates what we're changing to what we're trying to maximize or minimize in this case. So we need a way to relate the area of the parallelogram to x. So that's our first step. So we could use the area equation for parallelogram, base times height, right? If we know its base and we know its height. And now you could express base and height in terms of x using Pythagoras, right? Because they're both the hypotenuse. And you have x, and you have, what is that, 8 minus x. And here you have x, here you have 10 minus x. Absolutely, so you could use Pythagoras. That looks a bit messy to me. I think I would rather use the area of the rectangle minus the area of the triangles. Right, and then we're left with the parallelogram. Again, both would work. I encourage you to try the Pythagoras method and then base times height. I will use the area of the rectangle minus area of the 4 triangles. And just observing that, these triangles are the same and these are the same. So we could simplify it a little bit as well. Alright. So, area parallelogram equals area rectangle minus area triangles. Right, just writing an equation that, like a pseudo equation, just so I know where I'm heading. So the area of the rectangle, 8 times 10, width times length, which is 80. Nice. Minus the area of the triangles. So area of triangle 1. So area of triangle, half base height. So base of x, height of 8 minus x. Right, and we have 2 of them. So base, or excuse me, half times base, which is x, times height, which is 8 minus x. Cool. So again, in here, that is the area of triangle 1, half times base times height, and I put a 2 at the front because we have 2 identical triangles, right? 2 triangle 1s. The other triangle, actually, just to avoid confusion, I will subtract the other triangles as well, instead of subtracting the addition of the 2 triangles. So the other triangles, base 10 minus x, height x. So we have 2 of them, half times base times height. Great. And so that is our area. Looks a bit messy though, so let's simplify it. 2 times 2, that's great. So we're left with x times 8 minus x. Same over here. We're left with, I'll put the x at the front now, x and then 10 minus x. Looking better. I can see if we expand, we'll have some like terms. So let's expand and then group like terms. We get 8x. Now we need to be careful here with all these negatives. So x times minus x is minus x squared, but we're subtracting it, so that will be plus x squared. Then we have minus 10x, and like before, plus x squared. Grouping like terms, the x terms are minus 8x minus 10x, minus 18x, x squared plus 2x squared. Whew. I mean, that was quite a lot of work just to find the equation for area, so very algebra heavy. But from here, thank goodness, we can use our calculus. So let's just look back at the question. We found an expression for area in terms of x. Now we need to find the value of x so that the area is minimum. So minimum, we should be thinking turning point. Turning point, we should be thinking gradient of 0. Gradient of 0, we should be thinking we need the gradient function. Right, so let's find that next. So the derivative of a with respect to x, in other words, the gradient function, how a changes as we change x. Derivative of 80 is 0, because it is a constant. Derivative of minus 18x is minus 18. And derivative of 2x squared is 4x. Right, so that is our gradient function. Or we could write that as 4x minus 18. Right, just more conventional with the x term first. Okay, so that's our gradient function. What next? We're looking for the minimum, so we say min or max when the derivative or the gradient is equal to 0. Alright, so I'm explaining the step before I complete it. So I substitute in 0 for the gradient and I solve for x. So 4x equals 18. X equals 18 divided by 4. What is that? 4.5. Yeah. So when x is 4.5, it will either be a maximum or a minimum. Sweet. So So let's just pause here. Recap so far. We started off by finding the area equation relating to x. And in doing that and differentiating it, that would be achieved. We then acknowledged we should use that gradient function and set it to 0 to find the turning points. And we don't know if it's a minimum or a maximum, right? We assume it's a minimum, however, we need to justify it. So that's the excellence component. So let's do that next. There's so many ways you can justify this. I'll show you one or two. See how I feel. Right? It's not all about you. Sometimes it's about me. Cool. So, firstly, easiest way, in my opinion, is acknowledging this equation. So let's just have a think about that. So what type of graph would that produce? Right? X squared, so it'll be a quadratic, and it has a positive 2 in front of it. So the area would be a positive quadratic, something like that. For a positive quadratic, it doesn't have a local maxima, it only has the local minimum. And that could be our justification. Cool. So for example, actually, have we answered the question? Find the smallest possible area. Okay, getting ahead of myself. We found the x value at which that area occurs. What step am I missing? Finding the actual area. So, finding area when x is 4.5. So using that green starred equation for area equals 80 minus 18 times 4.5 plus 2 times 4.5 squared. Right, I'm putting that in on your calculator. Should be 39.5 centimeters squared, if the solutions are right. Cool. Alright, wait. So we found the area, the minimum area. Great. Now we need to justify that it is a minimum. So this is a minimum because our equation A, in terms of x, is a positive parabola which only has one minimum. Or in other words, no maximum. Yeah. And that is sufficient justification for excellence, in combination with finding that area of 39.5. Cool. Alright, another way you could justify it is you could find, so remember that derivative that we worked out, dA by dx, you could find, so you pick a number just to the left of 4.5 and just to the right. So for example, so the derivative when x is 4 would be, what is that, 16 minus 18 minus 2, and the derivative when x is 5 is positive 2, which says that to the left at x equals 4 it is decreasing, to the right at x equals 5 it is increasing, therefore minimum at x equals 4.5. Right, considering the shape of the derivative, in that it's decreasing and then it's increasing. Excuse me, the shape of the original function. Cool. I'm going to stop there because I'm really hungry. Have a good day.